All right, this is a special kind of truss, and I'm going to tell you right now this is called a K truss because you can see the letter K there, and there is a backward K here. So this is a K truss, and for this particular problem, so this is homework, first find the reactions. And then I say find FHI. HI is right here. Now, I give you a little hint. You can find it with an unusual cut. What I want you to do is see if you can find it with normal methods. And then I will show you an unusual cut where you can get FHI or this one or this one or this one quite easily with a simple cut. So in other words, if you're given this on an exam, for instance, the Fundamentals of Engineering exam or something like that, you can solve this very quickly to get FHI. But anyway, give it your best shot, and I'll work it next. Okay, so first let's find the reactions. So here's our free body diagram, and I'm not going to go through it. I can take moments about A. This is what we get when we take moments about A. We get BY is 2.92. Take moments about B. This is what we get when we take moments about B. I get AY is 0.083 kilonewtons. And we can take the sum of the forces in the x direction, and we get a x. So our final free body diagram for this looks like that. And now I will show you this unusual cut. So it looks like this. I'm going to go around here, then through here, and there I am. So there's an unusual cut. So it goes sort of around the middle of the K. You can see the K here, and what I want to do, the unusual cut here, is where we come around this middle part of the K. So if I use my copy and paste, what's it going to look like? I come in through here, and I cut through there, through there, through there, copy, paste. Well, what does that look like? It looks like this. And what do I have to do? Again, I have to put forces at each one of these. And I have one there and one there. So I have those four forces. And that's what I've illustrated here. So now that I have these four forces here, well, how can I want to get FHI. Well, how can I get it? If I take moments about C, what do I see? All these unknowns go through point C, so they're eliminated. And so that's the thing to do, is to make that unusual cut and take moments about C. And it ends up to be extremely straightforward. So moments about C, all of these forces disappear. So all that I have left are, well, this one disappears as well. Those two, that's it. So it's quite straightforward. And so I have 0.08 times 3, that's that distance right there, and then FHI times this distance here, which is 4. So that's also clockwise. So they're both positive, and I solve for FHI. It's negative 0.06. So this is the trick with a K truss. So you need to know this. You see it on an exam. You need to know how to make this funny cut with a K truss. Okay, so Here I've given you the reactions. Here's the homework. Find the force in member LM. LM is this one. And again, you can see this is a K truss. It's got these, then backward Ks. You can see it right here. Okay, so that's a K truss. So I showed you how to make the cut, so now make the cut to make this unusual cut to get LM, FLM. Okay, so pause the video, do that. And since I've given you the reactions, it's quite straightforward. So what do? I come in, I have to make this unusual cut that goes this way, then this way, and this way. And again, if I use my copy and paste, it looks like this. Copy, paste, and again, it's hard for me to find where to put this, but I guess I'll shrink it down. And so there it is. And again, what do? We look for where have we made cuts, and we're going to, so I made a cut here, so oops. I made a cut here, so I have a force here, I have a force here, I have a force here, and a force there. So again, I have those four forces. I take moments about this and I eliminate all those unknowns. And oops. So here's my free body diagram. I take moments about that point. So moments about n equals 0, and what do I have? I've got that force, and that force. So you can all see it here, and with one cut I'm able to get FLM is minus 13.3. Now, if I wanted to get this one, then I can do that too, but I take moments about L. So I take moments about L here. And when I take moments about L, well, again, I eliminate those two and this one. And so this is 0, so I don't have to worry about it, but what do I have left? I've got that one, I've got that one, and I've got this one. So those three are here, and you can solve for that. Notice that, here I am. If I didn't do this funny cut that goes along like that, it would be very hard to get this force, because I'd have to do a lot of work to sort of get there, in a sense. I would have to make my way, maybe do something like that and get these, and then I'd have to get those, and then it's just very difficult to do it, and then get those, and then so very difficult if you don't make that unusual cut. So that's the trick with this K truss. So you need to be able to recognize a K truss. And I'll just point out that this is a K truss. How do I know? Because if you look at it sideways, I've got a K there, and I've got a K here, and I've got a K here. So watch for the tricks. And again, what do you have to do? You've got to make a cut that goes like that. You might be able, so you can do something like that. Now, yeah, sometimes you don't even notice. Sometimes you don't even have to find the reactions. For instance, it's very obvious what the force in this member is, Of course, these are zero force members, and look for your zero force members. But the K truss is an easy one to work with. But I can see that this force goes directly into that member. So I don't need to find the reactions, for instance, to get the force in that member. So sometimes, just to let you know, you don't necessarily always have to find the reactions to get some member forces. And like we say, we even get zero force members without doing the reactions. Okay, I want to say something about truss stability and loading. So notice this is not a truss really, but we can see that it's not a truss in the sense that if I put a load on that truss, what's going to happen to it? Well, it's going to deform into this shape. It's not stable. It's not stable. And, like I've said before, we want to use triangles, basically. And how can I make this stable? Well, the way to do it is to put a cross member in like that. And then I could put another member here, but they both, this is stable with triangles. I'm not going to go into details. I have two hinges here. I really should have a hinge and a roller. Actually, maybe I'll change that just to be capable of doing what we're solving for here. So I'll put a roller there. And that is stable because now it's triangles. Now, I'm going to give you some info. So I'm going to number a truss with, the nodes will be numbered. Okay, so I want to illustrate what is stable, and we're going to start with 3 nodes. So, for instance, if I have 3 nodes, what do I make? I make a triangle. And I know that the triangle is stable. And notice that I want to see whether the number of members is going to be 2 nodes minus 3. So in other words, 2 times the nodes minus 3. And so in other words, for this one, I have 3 nodes, 1, 2, 3 nodes, and if I take 2 times 3 nodes, so I'm applying this expression, minus 3, well, what's that equal to? That's equal to 3, right? 6 minus 3 is 3, and that should be equal to the number of members for this to be stable. So, and how many members do I have for that triangle? Well, I have 1, 2, 3. So yes, this expression, members equals 2 times the number of nodes minus 3, that expression is true for this triangle. Well, I can create another truss that we know is stable by just adding another triangle to it. Now how many nodes do I have? So I now have 1, 2, 3, 4 nodes. So I have 2 times 4 minus 3. That's 8 minus 3 is 5. How many members do I have? Well, I'm going to have 1, 2, 2, 3, 4, 5. So that's correct. And so I can go even farther than that by adding another triangle here. And So I would have one more node, so that now my equation would be 2 times 5 minus 3, so that's 10 minus 3 is 7. Now, is that the number of members that I have? So let's check it out. So the number of members is 1, 2, 3, 4, 5, 6, 7. So the answer is yes. That's the number of members, and that tells me that I have a stable truss. So I can look at that. And for other trusses, for instance, so when we'll take a look at it and see whether or not we have some stable truss. So this is what we want for, this is what we want for a stable truss. And the number of members equal 2 times the number of nodes minus 3 for a stable truss. And then I want to reiterate that we do not put a load that's not at the node. Why? Because, like I say, truss members are long, skinny members. They only resist tension or compression. They do not resist bending. They're not beams. Beams are short, fat members. So in other words, if this member here, in a sense, were a beam, yes, well, we can load beams in the middle. We cannot load truss members in the middle because they're going to end up like that. So we don't do that. We load the truss only at the nodes like that. So okay, I'm going to stop there.